Okay, good morning. So welcome to the next lecture. And so I gave you the list of questions. And so for those who are not here, they will not know that the first question refers to E equals to mc squared. And then also, if you notice carefully that there is nothing about lecture 15. So lecture 15 is a bonus. So tomorrow's lecture is a bonus. And so it will not be in the interview. So you don't have to come if you don't want to. But I'm still hoping that at least one person will show up. All right. So we are in the middle of discussing some applications of general relativity. And so far, we discussed the gravitational waves, which is like one of the amazing predictions, and now finally tested. And then yesterday, we discussed applications to basically spacetimes outside of spherically symmetric distribution of matter. So if you have a spherically symmetric planet, or if you have a spherically symmetric star, then outside, when there is already a vacuum, the metric has to be the Schwarzschild metric by the Birkhoff's theorem. Okay, so now we can basically study astrophysics, you can study stars, and you can study what's happening outside of the stars, taking into effect general relativistic effects here. So now the next application is that of black holes. And so basically we are lucky that it's described by the same solution, by the Schwarzschild solution. But now the solution is taken not only outside of spherically symmetric matter, but it's taken for granted. We valid all the way to r equal to 0. However, the idea of black holes actually goes back much further. And so the first discussion of sort of black holes is already in the 18th century. And so it's not really black holes, but it's something like called dark stars. And so this is a concept John Mitchell came up with already in 1783, and then Laplace also discussed these things and so on. And so the idea is very, very simple. So this is just using the Newtonian physics and whatever. So you have a star with mass m. And so then you may be calculating what is the escape velocity from the surface of this star. So if I shoot something with some velocity here, and so if I shoot not enough, with not enough velocity, the thing will come back. It doesn't have enough kinetic energy to escape the gravitational field of this star. And so, of course, the escape velocity is telling you, well, I can escape all the way to infinity. So now, what this guy was saying, well, maybe there are some stars which are so massive and so, so big and so massive that even light cannot escape from their surface. Okay, so now I really shoot the light here, and the light, even the light moving with the velocity c, actually cannot go all the way to infinity. So now if you just do very, very naive Newtonian calculation, you say the light is a ball of mass m. It's a particle. At this time, there was this huge discussion whether light is actually a particle or whether it's a wave. So if you treat it as a particle of small mass m, then on the surface of the star, it has simply the kinetic energy 1/2 mc squared. And then it has the potential energy, which is minus gm m over, let's put capital R, or small r. So that let's put small r, which is the radius of the star. Okay, and so if this were to escape just to infinity and it would stop at infinity, this would be equal to 0. Okay, so now at infinity I have 0 gravitational energy and I have 0 kinetic energy, and so this would be 0. And from here, you can, of course, cancel m, and then you can solve for the radius of the star. And you find that the radius is equal to some specific radius, which is 2gm over c squared. Okay, so this is the radius for that star. And so if the star is more massive than this, then the light will not escape. And of course, this is a crazy Newtonian calculation, which is using the fact that the light is like a massive particle. which we know it is basically not. And certainly you cannot use this equation here. But what is funny is that this is precisely the radius of the black hole as predicted by general relativity. So this is the radius. So this coincides with radius of black hole. In full nonlinear general relativity. Okay, so this is quite amusing fact. However, what is really different is the interpretation. So interpretation is completely different. So namely, here we are really studying, how much energy I have to shoot the thing so that it doesn't come back to the star. But of course, no matter what I shoot outside of the star, it will go somewhere, some path, and then it comes back. But if I'm sitting here, I can already observe that, right? So if I'm sitting here, I will see that this thing was actually shot outside. But this is not what happens on the black hole. So on the black hole, if you shoot the light outside of the black hole, the light simply stays on the horizon of the black hole. It doesn't go anywhere. Nothing can leave the horizon of the black hole. Here, I just don't have enough kinetic energy to go all the way to infinity, but I can go somewhere. But on the black hole, I just stay on the horizon, no matter how fast I shoot it. Okay, but what it also means is that if I have an observer here, and he observes, yeah, I actually shoot something here, then this observer can have an agreement with another observer over here, and can let this observer here to know that actually something was passing by. So he can send another information to this observer, and that observer can send an information perhaps to an observer at infinity. So actually, even the observer at infinity can learn that something was actually shot out of the star. Okay, so the information can leak out here. So whatever is happening here, the observer at infinity, in principle, can actually get to know. Okay, so that's not the case with the black hole because, as I said, nothing really escapes from the horizon, so nothing leaves from that radius. All right, so it's just so for example, e.g., information can leak out all the way to infinity. To infinity with the help of your friendly buddies or whatever. Infinity. Okay, so that's not what happens in the black hole case. So anyway, so this was the idea in the 18th century. Of course, people didn't like it, but yeah, Laplace studied it independently. And the idea was here. And then it was, of course, rediscovered by Schwarzschild in 1916. Again, that we can have something like dark stars, but again, people didn't like the solution. The solution has problems that are equal to 2m. The metric becomes degenerate and so on. And so people didn't really, again, believe that this solution is meaningful until 60s. And we will discuss that today. So in full GR, in full general relativity, we have the Schwarzschild solution. The Schwarzschild solution, which I will write again. So it's ds square is minus f dt square plus dr square over f plus r square d omega square. So by the way, somebody asked me yesterday why I didn't choose r as a function of r and t. You can do it, but then you can always rename the coordinates. So whatever this was as a function of r and t, I just rename it to be a coordinate r. And so new coordinate is just a coordinate transformation. And then whatever I'm doing here in this 2x2 matrix doesn't really change. So this is without loss of generality. I can just choose r squared d omega square, where r is just one coordinate r. Doesn't have to be a function of r and t because I can always do a coordinate transformation. All right, so this is the metric where f is 1 minus 2m over r. Okay, and so this is the exact solution of nonlinear vacuum Einstein equations in the presence of spherical symmetry. And you see that nothing depends on time t, so it's static solution. So people were happy to use this solution for stars and planets and so on, because they knew that whatever is happening at r equals to r plus equals to 2m, which is a problem, is hidden underneath the star surface. And so it doesn't really, this metric really doesn't apply there. I have to use a different solution. I have to use the interior solution for the star, where there is some matter for the star. And so they were not bothered by that. But they were very reluctant to actually accept this, that this solution could exist as it is written here, all the way to r equal to 0. Okay, and so this is the problem, r equal to r plus. The solution seems singular. There's another singularity at r equal to 0. So now, can we actually, so what is happening here? So what is happening at r equal to r plus? And you'll see that very many strange things actually are happening as you start approaching r equal to r plus. And they are quite puzzling, they are quite counterintuitive, and you wouldn't certainly expect these things happening. And so instead of actually discussing this complicated case where we actually have this full Schwarzschild solution, I will first discuss these things in something much, much simpler and much more intuitive, and that's just the frame of an accelerated observer. So to get some insight, in fact, you get all the insight you need. To get some insight, let's study Rindler space. Okay, so Rindler space I introduced a long time ago. Simply, if you are an accelerated observer in Minkowski space, and then you transform to the coordinates associated with this observer, so you have some new capital X and capital T coordinates, then the metric actually is no longer flat, and it's interesting, and you study that in your homework as well. All right, so that actually, you will see that whatever is happening in this Rindler space will also be happening in the Schwarzschild case. And so I would basically say that this is really black hole demystified. So, we will see that whatever we understand in the Rindler space that is basically obvious explains everything what's happening near the black hole. Okay, so what is Rindler space? The Rindler space is we can just take the two-dimensional section, which is interesting one. So, and that reads whatever in your notes, 1 plus ax square dt square plus dx square. Okay, so that's our metric for the accelerated observer, and you derive it in your homework, and then we discussed it a long time ago. So now you immediately see that there is again a problem with this metric, and the problem happens when x is equal to minus 1 over a. So we have the Rindler horizon, where the metric is no longer well defined, and that happens when x equals to x plus equals to minus 1 over a. Okay, and so you see that the metric has a problem there. And of course, what it means is that if I am to understand this metric as it is, I have to limit myself to considering only x bigger than x plus. So my range of coordinates is t goes from minus infinity to infinity, but x goes from x plus to infinity. Okay, I cannot go through x plus because the metric is not well defined there, right? So now what I'm really trying to pretend here is that I don't know that this is just a transformation of the flat space. Well, I'll use that a little bit later, but okay. I'm pretending that I just start with I'm giving this metric here, and let's try to learn about this metric. And the first thing I learn is that this metric only covers x, which is x plus to infinity, because there is something wrong at x equal to x plus, which is equal to minus 1 over a. All right, so that's the Rindler horizon, and I cannot go through this horizon. There seems to be a singularity. Okay, so the next thing you can look at this, what is this surface x equal to x plus doing with the gravitational redshift? So let's say I have an observer who is sitting at x equal to x plus and sends a signal to another observer who is sitting at x equal to, let's say, 0. Okay, so this is called, so consider two static observers in Rindler space. And then calculate, what is the ratio of the frequencies they see if they send signal one to another. So they are static, so they are sitting at x equal to constant. And so the ratio of the frequencies, one observer is A, the other observer is B. So this is the nu, so that's the frequency, it's not velocity. It's equal to the opposite thing. So we are doing the same calculation for the gravitational redshift as we were doing before. So it's the proper time of B versus the proper time of A. And because these observers are static, they are not moving. They just sit there at x equal to constant. This is simply given by minus GTT at B and then minus GTT at A. Okay, that's the formula we have seen a long time ago. And so now, if you look at what your GTT is, so GTT is minus 1 plus AX squared. So minus is gone and the square is gone. So it's 1 plus A XB divided by 1 plus A XA. So A is the acceleration of the observer sitting at x equal to 0. Okay, and so now I can take the limit that, let's say, the observer B, so S XB approaches my horizon. I'll send the observer B be sitting close to the horizon, the Rindler horizon at x equal to x plus. So what are we finding then? What is this ratio equal to? Huh? 0. Perfect. We have that nu A over nu B goes to 0. So in other words, if the observer B, who is sitting on the horizon, sends a signal to an observer who is sitting at any other x, the other observer will see this infinitely redshifted. He will never see whatever that observer is sending. So this is, infinitely redshifted. So we have infinite redshift. And so for this reason, the Rindler horizon, that surface x equal to x plus, is sometimes called a surface of infinite redshift. Okay, surface of infinite redshift. So if I'm sitting on the horizon, I'm sending signals to anybody else in my Rindler space, they will not see it. It's just the frequency which they send it, which they receive, goes to 0. All right, so that's first strange thing which is happening, right? So on the horizon, whatever I send from the horizon, it's just infinite redshifted, it will never be seen. Okay, So of course, what it also means that the proper time of this guy, the clock of this guy, xb, goes infinitely times slower than the clock of any other guy in the Rindler space, right? So this guy is really, there is no time elapsing on his clock, whereas there is lots of time elapsing on any other's clock. Okay. Okay. So now let's draw some picture. So let's imagine an experiment that we have again the observer. So we know that the Rindler space looks like something like this, and so that the observer, let's say the observer at x equal to 0 is sweeping this trajectory. So this is x equal to 0, Rindler observer, and this is my horizon at x equal to x plus. But we can also draw lines of constant capital T. So one line of constant capital T is this one. This is t equal to 0. But then I have another line, let's say t equal to 10, and then t equal to 100, And do you know what line would correspond to t equal to infinity? It's precisely this one, right? So this would be t equal to infinity. And similarly, this guy would be t equal to minus infinity. So let's take it here. So this is the future horizon, that's the past horizon. Both of them are determined by x equal to x plus. Okay, so we have this picture for the space-time. And so now let us imagine that the observer, let's say here, he just releases a flashlight, and that flashlight just continues on the Minkowski geodesic all the way to the horizon. So now it moves on a straight line, and so this is my flashlight trajectory. So I have this thing, flashlight. It looks like a pacifier. It's supposed to be a flashlight. So anyways, okay, so this flashlight is simply moving now on a geodesic in the Minkowski space. It's not moving with acceleration. All right. So now the question is, of course, this flashlight is sending signals back to our accelerated observer. Okay, so the signals, because we are still in Minkowski space, but you can show it here as well, it travels under 45 degrees, right? So if I'm setting radial signal, it will just be traveling under 45 degrees. So which are the lines parallel with this guy? It'll be this one, that one, that one. Well, it's not parallel. That one, and so on. And so the observer sees, let's say, the first flash at t equal to 10, and then the next one he sees at t equal to 100, and the next one he sees over there. So now, as the flashlight approaches the horizon, okay, so this is how the light travels. Okay, so now as the flashlight approaches the horizon and sends the signal, so when do you think the observer will see this signal? It's later and later, right? So if I send the signal here, I see it at t equal to 10. If I see it at t equal to 100. I see it at t equal to 1000. But the signal which was basically released close to the horizon, I will only see at t equal to infinity. Okay? So what it actually means is that if I'm looking how this object is actually falling towards the horizon, what I see is that the object is actually slowing down its motion. Because more and more time elapses, in between this thing and that thing and that thing. And actually infinite time elapses if I want to all the way across the horizon. So you can see from this picture is that the object freezes on the horizon. the observer will never see the object, the flashlight, to cross the horizon, because simply, the object, from his perspective, reaches the horizon at t equal to infinity. Object reaches, just a second, reaches horizon at t equal to infinity. Yes?
I mean, I always get confused. Even in the homework, I got confused because this capital T is just a choice of coordinate, right? But why can I say that this is the time?
No, I'm just saying. No, I'm using this time coordinate here. So, okay, well, all I'm saying is that the object will see to cross the horizon at this t equal to infinity. However, remember that how we constructed these coordinates for the Rindler space. So if we have really an observer who is sitting at x equal to 0, then this coordinate time t was his proper time, right? So it's really his proper time. So he will see the object to cross the horizon at his proper time equal to infinity.
So can I call these lines the line of simultaneity?
So t, of course, yeah. So these t equal to constants are the lines of simultaneity for that observer. Yeah, exactly. Yeah. So isn't this amazing? So now you actually realize that whatever is happening with the object, it takes an infinite time for the observer, for the accelerated observer, to see the object to cross the horizon. Okay. So because of this property, when we will discuss the same thing for the black holes, first, these black holes, especially in Russia, were called frozen stars, because whatever you sent to the horizon of the black hole got frozen there. And so this was one possibility to call these objects, but in the end, actually, it was Wheeler who coined the term black hole, and then everybody liked it. So then actually frozen stars were abandoned, and now they are called black holes. But it's this property that whatever you send towards the horizon freezes on the horizon. It never crosses the horizon. Okay, so now the question is, what is really happening with that object on the horizon, right? Is it really the end of the space-time? Do all these objects accumulate there? So I send them there, and they simply accumulate there, and they never, So then this is like a big garbage place for all the objects which we send there. So what's happening is happening on the horizon. And whatever I'm going to discuss now is called also the maximal extension. Maximal extension of Rindler. So now, whenever you want to know what's happening, close to the surface where strange things are happening, the best way is to shoot at that surface some geodesics and to see, if these geodesics can survive, going to that horizon, going through the surface or not. So the idea is to shoot geodesics at the horizon, and see what happens. So now we can, in principle, choose any geodesic. So this is my horizon here. And so in principle, you can choose any geodesic which goes towards this horizon. What people like the most, and what is the simplest to analyze, is you choose the null geodesics. So simply how light would travel. So that's the simplest possible thing which you can actually do. And so instead of choosing an arbitrary geodesic, I just choose a geodesic which actually goes directly at my horizon. And the question is, can this geodesic pass through that horizon, or actually it terminates at the horizon? If it terminates at the horizon, and something really bad is really happening there. Maybe there's this garbage of all these objects. The geodesic will hit these objects, and then it will end there because it cannot continue through it. But so can we? So the question is really, can we continue the geodesic through? Okay, and so that's the idea of extending the space-time across the horizon. So if we can go through, and this is just, was something like coordinate singularity, it just tells me, yeah, there's just, bad coordinates. If it cannot continue through, it tells me, yeah, there's something really physical happening, which does not allow me to cross that horizon. All right, so that's the idea. So now to this purpose, let's study the null geodesics in the Rindler space. So the null geodesics simply have ds squared equals to 0, and then this is my equation, 1 plus ax square t dot square. That's the Lagrangian, which you are studying in one of your tutorials, and x dot square. Okay, so this is the Lagrangian, simplest possible Lagrangian you can write down. It's the g mu nu x dot nu. Okay, and so this is your equation, and now you see that I can solve t with respect to the x. So if you integrate, what you find is that t is equal to plus minus 1 over a logarithm 1 plus ax plus a constant. Okay, so this is the equation for a geodesic, where plus minus basically stands for whether I am shooting this geodesic, this radial geodesic, or that radial geodesic. So one of them will correspond to this one, the other one will correspond to that one. Why I'm interested in both is that I have two horizons. I have one horizon, which is the future horizon, which I want to extend through, but I also have the past horizon here, which I want to extend through. So now this geodesic will be interesting, because now this geodesic actually is trying to go through that horizon. All right, so now this is the constant, so that actually suggests that you introduce new coordinates. So going from capital T and capital X, you now just want to introduce the coordinates which go along the geodesic. Okay, so let's introduce a coordinate u, which is t minus 1 over a logarithm 1 plus ax. What I'm really doing is that I'm calling this constant now u or v, depending on whether I have plus or minus, right? And so the geodesic will have either u equal to constant or v equal to constant, if I'm considering this one or that one. Okay, so that's u, and then v is with the plus sign, so it's t plus 1 over a logarithm 1 plus ax. So this geodesic, well, this is my new coordinate u, this is my new coordinate v. So this geodesic, which is trying to penetrate this horizon, has v equal to constant, v equal to 0, let's say. And then this geodesic, which penetrates this thing, has u equal to constant. Yeah?
Is it okay if the transformation is singular, it's 1 x equal to 1 minus 1 over a?
Okay, very good. So at this point, I'm just, changing coordinates, and you will see, yeah, these coordinates are still singular, because you are right. So I'm just, I haven't got rid of singularity really. So this will be true in my Rindler space as long as x is bigger than x plus, right? So this is fine there. But x equal to x plus, there's still a problem, and of course these coordinates still don't go through this. Okay, so then what you find is that you just use this coordinate change, and you find that the metric now is e minus e to v minus u du and dv. Okay, so now if you look at this metric here, my coordinates u and v now can go from minus infinity to infinity. So u and v goes from minus infinity to infinity. However, if you look at where u is infinite, it's precisely here. So this point here as u equal to infinity. And so my coordinates still cover, and so that's what this one will have probably minus infinity. Well, that's plus minus infinity here. for V, doesn't matter. So anyway, so these coordinates still cover only this part of the space. Okay, so they don't go through because I just don't go through u equal to plus infinity. I cannot go through plus infinity. Okay, still only cover, so still only cover Rindler space. So now why is this the case? So now we have, these geodesics which are shooting at my horizon, but they still cannot go through because simply, the coordinate reaches infinity here. Okay. So why is this the case? Is that these geodesics equal to constant and v equal to constant, the coordinates u and v are not affine parameters for these geodesics. Okay, so affine parameter is the nice parameter which parameterizes my geodesic, right? So now I can actually try to find an affine parameter for these geodesics. And it's easy to see that well, whatever I write down will be easy to see. So affine parameter for, okay. So let's call one geodesic to be going in and the other, so this is the in geodesic, and the other one is the out geodesic. So now if you want to find an affine parameter, so affine parameter along these geodesics, so really to find a nice parametrization of these geodesics, then you find that for the lambda out, so this is my affine parameter for the out geodesic, and that's given by e to the v. And then for the ingoing geodesic, lambda in is minus e to minus u. Okay, so that's the affine parameter. So now look at the beauty here. So we know that the ingoing geodesic hits my horizon at u equal to infinity. Okay, so now if I plug u equal to infinity here, then lambda in is simply 0. Okay, so you just terminated your geodesic at a finite value of an affine. So in particular, so lambda in on x plus is actually equal to 0. So now you terminated your geodesic at a finite number of your a finite value of your affine parameter. But now, if you go through this 0, I can go to positive or negative, whatever, around 0. And you see that the geodesic simply continues there and doesn't see any problems. Okay, so now can continue through this. Can continue through this. And so for this purpose, I just introduced new coordinates. So v is simply equal to this affine parameter, lambda out, which is equal to ev. So that one will continue through this guy. And then u is equal to minus, so it's equal to lambda in equals to minus e to minus u. Okay, and so this suggestive, I'm just now choosing my new coordinates to be these affine parameters for the geodesic. And then if you use this change of coordinates, it's obvious that your ds square just becomes du dv. So now there is no problem whatsoever at x equal to x plus. And then I can look at this metric, and of course u and v, there's no problem to extending this to go to minus infinity to infinity. There's nothing wrong with this metric. But what it actually means is that I went through the horizon, through this one here, I went through that one here. You can even introduce, of course, this is just a Minkowski space, so and that's obvious. I can just use these things. uv over 2, and x is v minus u over 2. So you see that u and v are nothing else, and then the metric is, of course, the Minkowski metric. ds square is minus dt square plus dx square. Okay. So you see that v and u are just the light cone coordinates you used in your tutorial some time ago. And of course, yeah, so they parameterize simply the null geodesics in the Minkowski space. So u and v are just the radial geodesics in the Minkowski space minus dt square plus dx square. Right? So all I'm doing is I'm basically parameterizing the null geodesics in the Minkowski space, but I started from the fact that I couldn't actually, I shoot them through the horizon, but I couldn't extend them because the coordinates were screwed up. But if I choose the affine parameters along these geodesics, now I can go through and I just have normal geodesics in Minkowski space, right? All right, so this is the way how you extend through the space-time. And of course, if you now draw whatever the space-time actually is covered by these coordinates u and v, or by coordinates t and x, you obtain what is called a maximal extension. So maximal extension of Rindler. And in this case, we know that that's how we started this, that it's nothing else than the Minkowski space. But how it looks like is that now this is my coordinate u, this is my coordinate small v, or this is my coordinate t, and this is my coordinate x. And the region which I had previously covered by my Rindler coordinates is just this region 1. So this region 1 is the original, the one is the original Rindler. But then I recover also the region 2 and region 3 and region 4. And these are just simply the regions of my Minkowski space. And so before I only saw this was t equal to minus infinity, and this was t equal to constant, and this is t equal to plus infinity. And before I just covered this part of the space-time, and this was my horizon. And that's my horizon. All right, so this is how you would recover, basically, how you would find the maximal extension of the Rindler space. So you start really with the metric, which is given in your Rindler space. You only cover this part of the space-time, but now you study, well, there's a problem here on the horizon, so can I go through? And the best way is to shoot the geodesics and see if they can pass through or not. And so this is how it is done. And so now we see that we could go through, and we discovered the region 2, region 3, and region 4, right? But all these regions are inaccessible to the observer, to the accelerated observer, who can only see region 1. All right, so now we can answer the question, what's happening with my flashlight, which was simply going on like this, right? So you see that nothing is really happening with the flashlight. The flashlight simply goes through the horizon. Of course, if I just measure in Minkowski time, it will take a finite time, probably very small time, for the flashlight to cross the horizon, right? So if I measure in Minkowski time or in the proper time, so Minkowski time is the proper time of the flashlight. So now this will be like, I don't know, 1 second to cross the horizon. But of course, during that 1 second, that capital T elapses all the way to infinity. So actually, it's also flashlight happily crosses to region 2, and it's just moving on a geodesic, but Rindler observer is that long time ago. right? It takes an infinite time, and nobody lives for infinite time. Well, maybe we will someday, but all right. So funny thing is that whatever I'm saying here about the Rindler space, this is precisely what happens in the Schwarzschild space-time. This is precisely what happens for the black hole. So we will see that, well, we will not really see, I'll just tell you, is that the original Schwarzschild coordinates, they just cover exactly the region like this. There's a horizon, future horizon, and the past horizon. This horizon is a surface of infinite redshift. Whatever the observers can see in this region, they will never see anything cross the horizon. Everything will get frozen on the horizon. The objects can happily pass through the horizon if they move on geodesics or whatever. So they can simply go through that. The only tiny difference is that behind the horizon of Rindler space, there is really nothing. There is just Minkowski space, right? In case of the black hole, there is now a singularity. So there's a singularity here and singularity there. So now, of course, the object happily crosses the horizon, and they think, well, okay, that's fine. But now they suddenly hit the singularity. And that happens very quickly, and you will calculate that in today's tutorial how long it actually takes for the horizon to, after he crosses, after the observer crosses the horizon, how long it takes to get to the singularity. And so actually you can calculate it not only for geodesics, but you can make an estimate for arbitrary motion. So let's say the observer has infinitely strong rocket and is trying to escape from the singularity. So let's see how long actually she can live when she's trying to escape. Okay, so black hole case is exactly the same. But now we have singularity in region 2 and region 3. Okay, so that's the only difference. You just don't happily continue your motion on geodesics, but you just end up in the singularity. It's a curvature singularity, so there's huge curvatures, and they will eventually tear you apart. Okay. Are there any questions to this? Yes.
Given like a set of coordinates, how do you know if you have found a maximal extension?
Aha. So how do you know that you cannot extend even further? That's a good question. So here, well, we have Minkowski. There is nothing else than Minkowski. In Schwarzschild, you simply hit the singularity, which you know it's a conical. It's a curvature singularity, and so you cannot go through a curvature singularity. That simply you can't do it. So yeah, again, if you find something strange happening, at some point, then you try to shoot geodesics or something. If the geodesics cannot pass through, then you know that you already found the end of the space-time. Yeah. So as long as you find some strange things happening somewhere, where geodesics suddenly end or whatever, you should be looking whether you can extend through that or not.
Is it generally the case that you can always extend past coordinate singularities, but not curvature singularities?
Yes. So you can never pass through a curvature singularity. Yeah.
But I think you can do it by counting the killing vectors or something for the maximally symmetric spacetime, right?
Well, okay, not in case of Schwarzschild black hole. Or what do you want?
I don't know. I remember something like this. I was reading it. Then, if you count the number of killing vectors, there's a number. If it is equal to that, then it is maximally symmetric.
Well, that's right. Yeah, but it's not really answering whether I can really maximally extend the space-time through a coordinate singularity.
So I can find the coordinate system that from where I can calculate that many number of killing vectors, then it is the maximum symmetric spacetime, right?
Yeah, but it's a different question. Sorry. Or at least maybe I don't understand. Let's talk about it later. But All right, so now we understand the Rindler space. So let's look at the real black hole. So back to Schwarzschild. Is there a question? No? Okay, so we are back to our space-time described by Schwarzschild metric. And so we know that the horizon is located at r equal to r plus equals to m. And you can again show that this is a surface of infinite redshift. You will show that in your tutorial today. It's exactly the same calculation as we did for the Rindler space. We are just comparing whatever the two observers on fixed r in the Schwarzschild spacetime will see, and then we'll set one r to r plus. You find a surface on infinite redshift. It's a surface of frozen objects. So whatever you send to this horizon, you will never see across that horizon. And so the idea was to call this a frozen star. But then, thanks to Wheeler, it got renamed to a black hole. So certainly I think that the term black hole is more sexy than frozen stars. That's why people chose it. Okay. So anyway, what it is a boundary. So r equal to r plus is a boundary of black hole. And similarly to Rindler, so whatever is happening in the region 2, this observer will never see, right? So whatever is happening here, the light travels this way, but the observer can only see all the way up to here, right? So whatever is happening behind the horizon will never affect the observer. So cannot see anything below.
What do you mean by boundary of a black hole?
How do you want to call it? It's simply, you could call it a surface of the black hole, or you could call it, I don't know. So the region, okay, very good. So when you do the maximal extension, let's use some terminology. So maximal extension. So again, the idea is exactly the same. You shoot geodesics at this. You find the affine parameter. You change the coordinates so that they are the affine parameter along these geodesics. So now I just give you the result. This was done by Kruskal. I think it was a PhD thesis in 1960. Was it 60? 60. And so the change of coordinates is as follows. You have your coordinates r and t, small r and small t, in the Schwarzschild space-time. And then this is the final answer. So this is the affine parameter along one geodesic as equal to minus e to r star minus t divided by 4m. And then v is the exponential r star plus t divided by 4m. And then this r star is dr over f, which is r plus 2m logarithm r over 2m minus 1 absolute value. Okay, so this is the thing. So again, you have to first find the null geodesics in Schwarzschild, and that's where this r star comes from. And then you just use the affine parameter, and the affine parameter gives you this exponential And so this is whatever it was, your capital U and capital V. Okay, so it's trivial. So now we can extend through R plus. And the maximal extension, as I said, looks precisely like this. However, now you have the singularity at R equal to 0. So this is what you get. This is your coordinate U. And this is your coordinate V. And these are constructed so that the light travels under 45 degrees. So this is the light cone. It's really 45 degrees. And then this is my horizon, of course, R equal to 2m. This is also the horizon, R equal to 2m. And then T equal to constant line in Schwarzschild space-time looks like this. So this is T equal to constant. And then R equal to constant is this thing. It's R equal to, let's say, 6m. But now I can go through this horizon, and so I will have R equal to m here. And then I will have R equal to 0 here. And that's a true singularity. And similarly, you'll find that is R equal to 0 singularity here. And then this would be R equal to m. And then this is R equal to 2m. And then 3m, 4m, 5m, 6m, and so on. All right. And so you see again, so the original Schwarzschild system only covered, so they have region 1, you have region 2, you have region 3, and region 4, and now I named it differently. I don't know why. 1, 2, 3, 4. So the original Schwarzschild is the region 1, which is this thing. And then the region 2 is whatever is hiding underneath R equal to 2m. So region 2 up here is called the black hole region. It's called the black hole region. So this thing is called black hole. Here. And in that sense, R equal to 2m, which is this line here and that line here, is a boundary of the black hole. Okay. But notice that you have also this unexpected region 4, perhaps unexpected. You have region 4, and you have region 3. Well, we should have expected from that picture over there. But anyway, so we have these two regions here. So now region 4 contains the singularity again. And it has, again, the horizon at R equal to 2m. But you see that this is well, from this perspective, this observer, this is a past horizon. So things actually can go through this way, but they can never go inside. So here, the horizon is such that things can go inside, but they can never go outside. But here, things go outside and never go inside. So that's why this region is called white hole, because simply, black hole is called black because only things can fall in, but they can never escape out, right? So that's why it's like completely black. But white hole is something where things can go out and they can never go in. Okay, so that's why it is called. What the hell I'm writing? It's not a hole. Please tell me when I write something like that. It's like a presidency for my hole. All right, and then we have this region 3. And the region 3, if you look at it, is just like a mirror region of the region 1. And so indeed, you know, the R keeps increasing this way, and I have R infinity somewhere here. And so region 3 is another asymptotically flat region. Asymptotically flat region. Another one. But you see that whatever the observer is here can never communicate to the observer there. Why? Because this is my light cone, and so this is the light cone varied everywhere in the space-time. And so simply all the events in the region 3 are space-like, separated from whatever is in the region 1. So never, cannot communicate with region 1. Right? So the two regions are space-like separated, and they can never send any signals or anything. Questions? Okay, now we understand the black holes. There's one more funny feature, which is if you look at this diagram and look at the t equal to constant line, that's precisely the slides which I draw here. So then actually t equal to constant slice penetrates both, penetrates region 1 and region 3. Right? So at t equal to constant, I now describe both regions. And of course, if I go very, very far away for large R on one side, I have asymptotically flat region. And if I go very, very far to the left, I have another asymptotically flat region. Okay, so this is something like, and then something, you know, happening in the middle as R equals to 2m. So at the center, I have R equal to 2m. And so there's some non-trivial curvature or whatever. And so it may be fun to actually look at this surface and try to actually, you know, so-called embed it in Euclidean space and see how the geometry looks like. So basically, we are trying to understand the shape of the geometry. And this is called Einstein-Rosen bridge. So t equal to constant surface is called Einstein-Rosen bridge. Einstein-Rosen bridge. And so what you can do is that you can, so we have the t equal to constant region, and then we have still too many coordinates. We have theta, phi, and r coordinates. So we know that everything does not really depend on where you are. So let's choose also theta equal to pi half. Let's choose that. And then you can try to embed this. So this is called embedding diagram. In Euclidean space in 3 dimensions. And so embedding diagram is something like how it describes how the geometry looks like. Geometry looks like. Okay, so now you will study that in your today's tutorial. You will do explicitly this embedding diagram, and you will construct it yourself. Here I'm just giving the answer. And so what happens is that you have one asymptotically flat region. And then you have sort of like a starting throat here. And so this throat goes like this. And this goes to another asymptotically flat region. Okay. And so you have, let's say, is the asymptotia of region 1, and this is the asymptotia of region 3. Okay, and then we go all the way to R equals to 2m, which is this neck here. And so this thing looks like a wormhole. Okay, so wormhole is something which goes from asymptotically flat space through some throat. So this is throat. Or neck, or whatever. And then, you know, we have one asymptotically flat space here, and connected is this tunnel to another asymptotically flat space here. And so it's like, looks like wormhole. So wormhole by definition is really thing which connects two asymptotically flat regions. And of course the question is, can you, well, it would be really nice to find wormholes in our universe which would connect some, you know, us to some very distant stars or whatever, so that we can take a shortcut and travel through this wormhole. Of course, this wormhole is not good because all we are describing is t equal to constant slice here. And so whatever the geometry is, it's space-like geometry. So there is no time in this picture, but everything here is space-like. So we can never travel through this wormhole because the whole thing is space-like. Cannot travel through. This is just a spatial geometry which we are plotting here. All right. So let me just know one funny thing is that, you know, the wormholes like this. Okay, so this has been known a long time ago. So Einstein and Rosen, that's probably, I don't know, it's definitely 60s, but probably less than that. But now actually people got excited about these wormholes again. And so you can plot similar wormholes, but now in ADS space. So now you just add cosmological constant to the black hole. So you will have Schwarzschild ADS, and then you can study the wormholes. So at present, such wormholes like this, wormholes like this, are interesting from the ADS-CFT correspondence, ADS-CFT correspondence. And basically what people suggested is that how long this neck is related to holographic complexity, the complexity of quantum field theory. So the length of the neck, is related or describes holographic complexity. Of course, this has to be in ADS, holographic complexity. So nobody knows what complexity really is. My former supervisor says, well, why people study complexity, why they don't study simplicity, right? Or something like that. But yeah, so then they're trying to actually, and so lots of people at PI are actually doing this. So that's, you know, one motivation for your essay. You can study holographic complexity. So the first idea was that really, you know, the system on the boundary, the quantum field theory on the boundary is more and more complex the longer this neck is. So that was the first proposal, and then it went to a slightly different proposal about the action in some region of the space-time. But anyway, so this is somehow related to holographic complexity. Questions? Yeah?
Can you make like a fake monopole next to a black hole, like a magnetic monopole or something like that?
Fake monopole.
Yeah, well, just by like letting field lines just go in or something like that, because then the divergence would be.
Well, the monopole has the Dirac string. So how do you get rid of the Dirac string? Yeah, I don't know. Let's discuss that later. You know? All right. So we have this, and so that's all you need to know about Schwarzschild black hole. So the last thing is that I would like to discuss a little bit more about the astrophysical black holes. And so the basically only difference is that here we just described the purely vacuum Schwarzschild black hole. But the real black hole, first of all, it was somehow created in our universe. So probably it was created by the collapse. So if it were created by the collapse, then basically the collapse automatically kills the unwanted region 4 and unwanted region 3, and all it remains is the region 1 and 2. Okay, so the astrophysical black holes are not expected to have the wide hole region, and they are not expected to have another asymptotic region 3. It's just a statement. Another statement is that, of course, once you form this black hole, then this black hole is not isolated. And typically you have lots of matter around the black hole, and this matter eventually gets sucked into the black hole. And this typically happens in the form of the accretion disk. So a note on astrophysical black holes. So first of all, these are typically formed by gravitational collapse. Of supermassive stars or something like that, and then regions 3 and 4 do not exist. So, yeah.
Why does the gravitational collapse imply that 3 and 4 don't exist?
I'm not proving that. So basically, what happens is that just very intuitively, you start in this region, and then you have the star, and then this star sort of goes like this, and so whatever is hiding here. So this is the surface of the star, and the star is sort of like making this thing here, and eventually forms a black hole here. So whatever is underneath doesn't make any physical sense because it has to be replaced by the interior solution of the star, right? So I start with some solution of the star, which means outside I have Schwarzschild, but inside I have some interior solution. Now the star starts collapsing, but everything what is basically on this side is hidden underneath the surface of the star, and it's never physical. So that's the idea. All right, so that's one thing. Another thing is that they typically rotate. Typically rotate. And so Schwarzschild is not really a good approximation. You actually now have a black hole, and there is a uniqueness theorem, and the theorem says that there's only 2 parameters which describe such black hole, and that's the rotation parameter, and the mass. So now this is really, really beautiful. This is encoded in the uniqueness theorem. And the uniqueness theorem basically tells you that if you have isolated black hole which is rotating, there's only one, and it's described by Kerr geometry. Kerr was found in 1963, and it's described by only 2 parameters, which is like really amazing. So if you take a star, so star has typically all the multiple moments you can imagine, right? So all the multiple moments will be there. There will be a dipole, there will be a quadrupole, there will be something else. All these things will be independent in general. However, for black holes, you can show that basically everything is determined only in terms of the 2 parameters. So all the multiples are already determined out of these 2 parameters. So it's really, really restrictive. So the black holes are really, boring, and So again, Wheeler coined the term that the black hole has no hair. So no hair theorem. And basically what it says is that if you started with a star with arbitrary multiple moments, these multiple moments have to radiate away. And then you just get one unique prescription for how the black hole, final black hole, looks like. And it's entirely describable in terms of the two parameters, A and M. Well, that's not entirely true. You can also have an electric charge, but electric charge is typically astrophysically not interesting, because if you have charge object, it tends to actually attract other charges to neutralize it. Okay, so if you have, so isolated black hole can be charged, but if you have some surrounding plasma or whatever, it will get discharged very, very quickly. Okay, so charge can also exist, and it's in that charge, meaning electric charge, is not typically astrophysically interesting. Astrophysically interesting. It's interesting from a theoretical point of view, but from an astrophysical one, not really. All right, so then they are not isolated, so not isolated. And they typically accrete matter in form of the accretion disks, in terms of the accretion disks. So then you have the black hole here. The black hole is in general rotating. And then the matter, let's say I have a companion star here, and so the black hole, gradually sucks the atmosphere of that star. And because this is typically in binary system, and so the matter from the original star has some angular momentum, so it doesn't fall directly to the black hole, but rather actually inspires around it. So then you have a picture like this. You have the accretion disk around the black hole, and so the matter gradually is going like inspiring slowly down to the black hole. So now why is it inspiraling? Why is it though it doesn't stay on the same radius? It's because there's a friction, and as you have various layers of the accretion disk, so the inner layer is moving more quickly, the outer layer is moving slowly, and so there's a friction. And so due friction, we have, first of all, this radiates a lot. And second of all, it's slowly moving inward. All right. So now this is happening as long as we can have stable circular orbits around the black hole. Okay. So now remember the graph yesterday. So we studied the potential for massive geodesics. And so the potential had two possible forms. So one form was that we had that inflection point, and so the potential either looked like this thing here. It had a minimum and it had the maximum, and then it went like this, or it went directly down there and it was not boring. So only in this case you can have stable circular orbits. So as long as you are somewhere here, that describes your. So this is for given angular momentum. So for given angular momentum, I'll be on that radius. So for different angular momentum, this picture will slightly change. So let's say it will change like this. And so that then, like this, then I'll be here, and so on. So then I'll be getting closer and closer. Okay. So now, the question is how close you can go to this black hole, and the answer is as close as the inflection point. Okay, so this inflection point is shown that has the radius r equal to 6m. That's what we shown yesterday. Okay, so the closest circular orbit, which is the stable one, is actually 6m. Okay, That's called R ISCO. ISCO is 6m for Schwarzschild. So ISCO stands for innermost stable circular orbit. Innermost stable circular orbit. And then for Schwarzschild, this is at 6m from the black hole. All right. So this we understand now. So that means actually that you can be on circular trajectory only when you are further away than 6m. But at 6m, you cannot be on the circular trajectory. If you are closer to this, then you just simply fall down to the black hole, right? So let me put this up. And this down. So that means that actually all the way up to 6m, I can have the accretion disk here. So this is my accretion disk. But then there is this R equal to 6m, which is the R ISCO. And then below, the accretion disk simply cannot exist because the matter simply falls down to the black hole and cannot exist on a circular orbit anymore. Okay, so now this is actually a very interesting prediction of general relativity, right? So there's this, inner boundary of accretion disk. Accretion disk, and this innermost stable circular orbit is, and that's R equal to 6m for Schwarzschild. If you have rotation, it will be slightly different, but let's say you have small rotation, then it's R equal to 6m. So now this is a unique prediction of general relativity. It's exactly at R equal to 6m. Okay, so now people can go and test it, right? So now they actually have the technology. They can look with the telescope, close by to the black hole. In fact, they are looking at the Sagittarius something, and so that's a supermassive black hole in one of the galaxies. And so now the resolution of the telescope is actually so that they can actually see the, inside the accretion disk. They can see the inner boundary of the accretion disk. So this the experiment is called Event Horizon Telescope. Event Horizon Telescope. And the aim is really to measure whether this inner boundary of the accretion disk is precisely as predicted by general relativity or whether it's somewhere else. Okay, and so that's a direct confirmation or disprovement of general relativity. Okay, and so we will see the results in hopefully soon. And some people at PI are involved in this. So Avery Broderick is involved in this. So if you are interested in things like that, then go and talk to him.
How do you know, like, don't you still expect matter to be within R equals 6m?
Well, yes, but that matter won't be on circular trajectory. It will be simply falling down. As it's falling down, it doesn't really radiate. So you have lots of radiation all the way produced in this accretion disk, but as the matter simply falls down, here it doesn't really radiate. So that thing is really much darker than the rest. All right, so we'll be testing this very soon. So by the way, until very recently, people just said, okay, I have this really. So what they can measure is the mass of the object really precisely, right? But they don't know whether that's black hole or not. So until very recently, people said, well, it must be a black hole because that's the only theoretical explanation, as long as you measure the mass and the radius was, let's say, smaller than 1,000 times the Schwarzschild radius or something like that. That's what they could see, that the radius is actually smaller than 1,000 times Schwarzschild radius. But now, actually, the resolution is so good that you can see, 6m. So really close. You can really resolve this. And this is really amazing technology, I think. There was a question? Yeah?
So, because of this frozen star property of black holes, won't we also see the light that's just sitting on the horizon?
Yeah, but it's infinitely redshifted.
Okay.
Yeah. So really, so black hole is really black, because everything, what it's sending, even from its neighborhood, it actually gets redshifted.
But like as you move away from the horizon, between the horizon and 6M, like it'll be less and less redshifted.
Yeah, no, but this is like really something which people expect to see. That's right. Yeah, your reasoning is right. But this is like really a huge difference in intensity in this region 6M,
Okay.
and the redshift actually won't be that huge still. So the redshift, so the closer you are, the redshift is bigger, but it's like really going. Yeah. So it's a good point, but still people can't believe that they can see this. So finally, what is really funny is that if the black hole is rotating, then typically jets get produced. And so you have like this huge amount of energy coming from so the black hole is rotating this way, and so you have these huge amounts of energy coming from the black hole. So this is called jets. Interestingly, people still don't know theoretically how these are formed. So maybe now there was a progress in simulations, but for a long time, people doing the numerical simulations, they couldn't see the jets production, so the code always broke down when they were expecting to see the jets. So maybe now there has been really progress, and now what Luis was showing you is actually the numerics. I doubt it, but maybe it is. You have to ask him. So these jets, they are observed astrophysically, but people couldn't, simulate them numerically, and people don't really know the mechanism which is driving the jets. So there is a mechanism which is called Blandford-Znaiec effect. So perhaps Blandford-Znaiec effect explains the formation of jets. And what it really is that you have the plasma, which so this thing is like a plasma, and the plasma is typically magnetized and it carries some magnetic lines. And so Blandford-Znaiec effect basically tells you if the field lines of the magnetic field can penetrate the black hole horizon, they can extract the energy out of the black hole. So this black hole is rotating and it has lots of rotational energy. So now, typically from normal black hole, which is non-rotating, you cannot extract anything. But once the black hole starts rotating, you can actually extract its rotational energy. And so the idea is that these jets are actually formed out of this rotational energy of the black hole. And there's some interesting interaction of the magnetic fields with the black hole, so that actually these jets can be produced. And so if you are interested in Blandford-Znaiec mechanism, so just look it up somewhere in Wikipedia, and then you can read about this. It's like really a mechanism how to extract energy from a rotating black hole, rotational energy from a rotating black hole. All right, are there questions? Yeah.
How about the innermost circular orbit for the current?
Oh, very good. So you can calculate that. I don't remember what.
Different?
Oh, it must be different. It must be different. It will depend on the rotation parameter A. But I don't remember the formula. But I can look it up next time. 100%. I'll do that next time.
It's bigger or smaller?
I don't remember. Sorry. I'm sorry. But yeah, so once you have so 6M is only for non-rotating, and it's very simple. It follows from what we discussed yesterday. If you have rotation, this thing will be postponed. So now we have to measure both things. You have to measure the mass of the black hole, and you have to measure how fast it is rotating. Then you can predict the innermost stable circular orbit, and then you can compare that to whatever you see by this telescope. Other questions? I promise I'll show it next time. All right, so that's black holes. So thank you so much. And then we will have funny tutorial this afternoon about black holes.